introduction. Thanks a lot to the organizers for putting together this very nice program workshop, and thanks a lot for inviting me to come and give a talk today. So I actually changed the title a little bit to just more specific on development of macroscopic monolayers, moiré structures, and nanoribbons. I come from a chemistry background, as you can see, so this topic is a little bit different than the previous talks. So this will be more about the development of the very large area materials, which I hope that can be helpful for the future experimental development of integrating this into the cavities to really see the predicted quantum phenomena. So this is not working. Okay. All right, so I believe we don't need further introductions about the 2D materials. We have heard a lot of wonderful talks earlier today and also earlier this week on the different variety of two-dimensional materials and also the possibilities of stacking the different materials together, like what you heard earlier today in Professor Zhou Yu's talk. And also these exciting opportunities for the twisted bilayer structures and to have this beautiful moiré patterns from the interference of the lattice structures that leads to a lot of the strongly correlated phenomena. But the one thing I have to emphasize here is that so far the size of these monolayers and moiré structures that people use in their devices to see this quantum phenomena are only to the size of tens of micrometer, which is like a cross-section of a hair. And that is actually not so convenient to incorporate with a lot of different types of experimental techniques, which you require either large beam spot size or large diffraction volume to look at their dynamics. Another challenge in this field, especially for the twist bilayer moiré structure, is that when you put these two monolayers together, first of all, the size is already very small. And also, there are usually a lot of contaminations that it will sandwich between the two layers. That will lead to a lot of the bubbles and inhomogeneities of twist angle across the crystal surface. So as a result, when you look at these papers, it's more like they have to make hundreds of different types of materials to select one that works, and you have to make sure that this little device would work on the small area of the sample. And I see many people sharing one sample between multiple groups because it's very hard to find one sample that works. And another critical thing is that this magic angle or this true correlated phenomena, this is for twist bilayer graphene, only appears in a very narrow angle range. It's actually close to like 0.1 degree range within 1.1 degree of magic angle. So can we make moiré structures over a large area with uniform twist angle and very clean interface? So there has been a lot of development on the different techniques to make these monolayers or the moiré structures to a larger scale. So this is actually a quick summary about the different techniques to make different monolayers at different length scales. So there are generally two different strategies. One is the bottom-up growth technique that will be more like chemical vapor deposition. The other is a top-down exfoliation. So there are a lot of developments on the chemical vapor deposition technique, but so far the highest quality monolayer and twist bilayers are still made by the exfoliation technique. So a few years ago, we have developed a technique to create very large area monolayers, single crystal monolayers with dimensions of millimeter to centimeter scale. We use a technique that is called gold tape exfoliation technique. So this actually takes into advantage of the strong adhesion force between gold and the monolayer. That adhesion force is way stronger than the interlayer van der Waals force that hold the bulk crystal together. So using gold, we can exfoliate monolayers to a very, very large area. And we initially make this work for a variety of transition metal like calcinite, and recently we have also made this work to create millimeter-sized single crystal monolayer graphene and HBN flakes. So That is all fantastic. So what can you do when you have a very large area monolayer? So we can actually couple these monolayers into a lot of different photonic devices. For example, we have coupled them into these plasmonic structures and also these photonic metal surfaces. All of these are actually enhancing the light-matter interaction so that we can either tune the output light, switching them on and off with a gate voltage, or enhance the spin value polarization in the emitted light, or we can build them into a cavity and try to lighten up some of the PL transitions which you cannot see in just an isolated monolayer. And of course, you can also use these large area monolayers and use them as a material to directly write these photonic patterns on top of it. For example, we can make an atomically thin lens to focus the light. So all of these are very exciting. And there are some other things we can do with these monolayers, especially when the monolayers are large enough. You do not need to use microscope objective, and also you can also use a lot of the far field measurements to couple with it. So one of the things we have done with this very large area monolayer is we use them to look at the strong field induced physics, and in particular, this is the higher harmonic generation. We send a very, very intense mid-IR light onto the monolayers or some heterostructures, and we see higher harmonics of them. And this is done in collaboration with Shambu's Gimaris lab in SLAC. And with this, we can see, in addition to the second harmonic, where people are usually seeing these structures, now we see up to 15 harmonic orders with different intensities. We can analyze their phase, and we can also look at they can also tune the relative intensities of even and odd harmonics by stacking the monolayers into AB and AA stacks with and without the inversion center. And we can also use them to study the flow case space of the 2p of the Rydberg states of the excitons. So all of these are already published. And today I'm going to share with you some of the unpublished ongoing work of what else we can do in making these 2D materials in a very, very large scale, and to open up more opportunities like what we have done on monolayers, and what can we do in the future if we can make this larger and larger, how can we couple them into cavities? So, as I have shown to you that beyond the monolayer, the twist bilayer is very exciting, and there are a lot of opportunities you can think about for the moiré structures. First, so the current challenge of making moiré structures is, if you start from the Scotch tape exfoliated monolayer, it's very small and the yield is extremely low and the size is very small, but the quality is usually better. And if you synthesize them from the chemical vapor deposition growth technique, it is very hard to control the twist angle. So you cannot really grow a magic angle twist bilayer graphene just from chemical vapor deposition. So we're trying to find a technique to create moiré structures with large yield and high angle controllabilities, big size with high efficiency and high uniformity. So what we do here is we use a similar types of technique, which is using the surface of gold to exfoliate the monolayer from the bulk crystal. So when we peel off a monolayer from the bulk crystal, that surface of a monolayer is freshly cleaved from the van der Waals interface inside layered bulk crystal. So that surface I would expect would be the cleanest surface you would achieve for any types of these monolayer surfaces. So we just take advantage of that super clean interface of the pristine bulk crystal, and we twist that at a small angle and just put it back. So with this, we can actually create a twisted van der Waals interface at the top layer of a bulk crystal, and that would be the cleanest twisted interface we can ever achieve. So with that, we can actually create a twisted van der Waals interface with that lateral dimensions of millimeter to centimeter scale. And we can randomly sample 4 different locations, and this is piezo response force microscope or torsional force microscope, whichever name you call it. So what you see in here, these are not atoms, but these are actually moiré structures in the real space. And from the periodic pattern of the moiré structures in the real space, we can back calculate the twist angle. And you can see that the twist angle is very consistent across centimeter scale surface. So we send this manuscript to Nature Communication. Unfortunately, it was recently rejected. One of the comments is that 4 points is not good enough to show them. So I asked my students to continue this effort, and he spent a day sitting in front of the PFM machine, and he collected up to 22 different locations, and now we can have a statistical variance of the twist angle across centimeter surfaces, and that statistical variance of the twist angle is 0.05 degree.
Aren't you left with some contamination on top of on the top layer because of
That's a really great comment. Yes, that's a really great comment. I'm glad you have asked about that because I forgot to say about that. So this is the AFM image of the surface. It's actually very clean. The root mean square is 300 picometer. And we also done an XPS on the surface to see if there is any remaining gold, and we don't see any gold signal on the surface. So this chemical removal of gold is complete. The reaction is very efficient, 100% yield. Okay. So, yeah.
Just a quick question. What about the other surface? The one that you are probing, the one that you're probing on top. Don't you have any contamination from the environment? I mean, if you expose the surface within seconds, you will have.
Yeah, this other surface. This other surface was also freshly cleaned. So we are actually combining the freshly cleaned surfaces back together. And you're right, we have to do this very carefully in a very clean environment and do this very, very fast. Within 1 second, pick it up, rotate, put it down right away.
In which atmosphere do you do that?
We do that in the glove box. And we have also done that in clean room. And recently my student was getting more lazy, and we are also doing this in air. And it turns out that if you do this in air, as long as you do this very quickly, and the surface is still very clean.
So it means that the surface is really not that reactive?
The surface is not that reactive. That's because this, that's a nice way, that is the nice thing for the 2D materials. The surface, there is no dangling bound, and this is atomically flat, and all the bonds are saturated, so it's not really chemically active to bond to these species. But of course, if you leave the surface in air for a long enough time, like what the other people have done in the pure and stack method, in that case, you would expect to see a lot of contaminations.
Thank you.
Okay.
So just to follow up, you don't need to encapsulate with boron nitride, or are you putting boron nitride on top?
So right now, we don't have any boron nitride on the top. We are just looking at the moiré structures as itself. But of course, if I want to look at the transport phenomena, and in that case, I need to really isolate this from the environment. I need to do that either in vacuum or encapsulated with boron nitride. So now our problem comes with, like, how can we find a large area of boron nitride to encapsulate it? There was this.
Are the angles still consistent once you take it off of the gold?
Yes, the angle is pretty consistent, like when we twist it and also when we take the gold off. I will actually talk about the stabilities, chemical stabilities of this small twist angle later on.
In the technique by Gorbachev, where they use a silicon nitride membrane covered with gold, which has some similarity to what you're showing. I seem to remember they had an issue making twisted stacks because of relaxation. Of course, I'm guessing this is a different temperature, but could you comment on that?
Yeah, so that was different temperature and also different size. Maybe, well, seems many people have asked about this stability, so let me just go ahead to this very last slide talking about the stabilities of the surface. Here we go. Sorry. Just look at here. So this is the electron diffraction of the moiré patterns, and you can look at the main Bragg peaks and to look at the twist angle. So many of you have mentioned the stabilities, and that is indeed one of the major problems in the field of twistronics. The small angle twist bilayers, in particular if you have a small angle of less than 10 degrees, that small angle of twist bilayers is not the most chemically stable format. The most chemically stable format is when they are twisted back, locked to 0 degree or 60 degree when you have the atoms right on top or perfectly avoiding each other. So the energy it takes to go from the few degrees to 0 degrees, that energy is actually dependent on the size of the flake. If you have a larger size of flake, you can imagine that the atoms has to travel a longer distance to go back and lock to 0 degree twist angle. So if we can make this twist bilayer van der Waals structure to the areas of millimeter to centimeter scale, then that would actually enhance the thermal stabilities a lot. And we have actually done this because this is a very crazy experiment, and people can never imagine this with twist bilayers. We have heated up to 500 degrees Celsius for hours, and the twist angle does not change.
This is great. Can you comment on the prospects of doing double gating of these structures?
Yeah, so that is actually a really great question. So this structure I'm showing you, this is just a monolayer on box structure. So if we are gating this, my student is actually working on how to gate this structure. Unfortunately, because of this huge piece of bulk underneath it, we can only do this on the top gate. But we have, I'm going to talk about this in the next slide, and there are also some other developments of how to make twist bilayer structures. And in that case, if you have a thin bilayer structures, you can put more of the gatings on them.
Yeah, great results. So the lattice relaxation effects are most pronounced at very small twist angles, like in graphene, you'd be like at the magic angle 1 degree. And so, does your technique also hold up over such large areas at like really small twist angles, or is it only at the larger angles where it's stable?
So we have actually we have tested thermal stabilities for 2 different angles. So the stuff I have just showed you, that is 6 degree. And we have also done another test at 2 degree twist. At 2 degree twist, if you heat it up at a certain, at a similar type of conditions, the twist angle would relax very little bit to like less than 0.1 degree after we heat it for hours. So if you can imagine this for the twist bilayer on the micrometer scale, they would relax and back and lock right away.
Okay, thanks.
So maybe to complement Jang's questions, at larger degrees, do you have any issues of like super lubricity that people see in these bilayer systems if they're very clean?
That's a great question. Actually, that is another collaboration project I'm doing with Tony Han's lab, and they are trying to use these very large area monolayers to study the super lubricity between the surfaces. So one of the problems that we have is in here, if the surface is very large, we are having trouble to put it onto a large enough substrate, and can have a really flat surface. All of the substrates that we have are so far rough, very rough. And these monolayers would be quite delicate, and they are quite sensitive to the substrate's roughness. Yeah, that was another thing that we are actually doing right now. Any other questions? Okay, great. I can move on. So we have actually used the same technique to create a great variety of different moiré structures from different materials, and all of them are in very, very large scale, either twist bilayer graphene or twist bilayer boron nitride, or all of these combinations of transition method like calcinide, and you can see beautiful moiré patterns on almost every one of them. And then now here comes the question, right? So the monolayer on box structure, as you have mentioned, it can only be capable for top gate devices. So how can we make twist bilayer structures? It's just purely bilayers. So the trick is the same. We can also just freshly exfoliate the monolayer from the bulk crystal. So now instead of putting this back onto the same bulk crystal, we put this back onto another piece of the freshly exfoliated monolayers. So now this surface where these 2 monolayers touch will be the cleanest surface of the monolayer touching the cleanest surface of a monolayer. We stack them together before they got in contact with other stuff. So with that, after that, we can also remove the gold on both of the sides, and that would actually leave alone a very, very large area of twist bilayer And the lateral dimension is also millimeter to centimeter scale. For these twist bilayers, one of the challenges, again, as I have mentioned in answering your question, is one of the challenges that we have for this twist bilayer is usually people put twist bilayers onto an HBN flake and then characterize the PFM. Sorry.
So maybe I'm missing something, but how do you determine which layer it adheres to, the top or the bottom, and how do you remove the gold only from the bottom and not from the top, like it shows in H, I think?
Here, H.
Yeah.
Yeah. So here we put two monolayers together, and you have, yes, you have gold on the top and you have gold on the bottom. So what our trick is, we make the top gold very thin and the bottom gold very thick. So the top gold is only around 50 nanometer, and then we can control the etching rate so that it etches the gold on the top and leave alone most of the gold in the bottom. And then after that, we will just flip it and put it onto the substrate. And then after that, we play the same trick of removing the handling layers and removing the top gold and etching the top gold again. And actually, it's not that crucial. Sometimes the bottom gold is etched a little bit, but we don't really care about that because there are also other handling layers that will hold the monolayers, and we are not losing them. So we put this twist bilayers onto the substrate, and here is the PFM or TFM images you see on the moiré pattern. So you might realize that the moiré pattern we see on here on the bilayer is not as nice as twist the monolayer en bulk. This is because our substrate is just a piece of silicon and it's very rough. So I would really, really love if anybody of you can recommend some flat silicon substrate or some other substrate that's very, very, very flat over millimeter to centimeter scale, and then we would love to try them out. So that is actually something that I really need to get some suggestions about where to buy this very flat substrate. So what are these large samples good for? Well, if your samples is large enough, you can do a lot of things from, like, for example, the far field spectroscopy, or you can also do a lot of other techniques like the X-ray scattering, or, I don't know, terahertz experiment, but without really need to focus the terahertz to a very small spot. So one of the things that we were trying to do in this very large area samples is, the first thing is we are actually using them for the angle resolved photoemission spectroscopy, and with that, we can actually clearly see the backfolded moiré structures at the K-point valence band. And you can see that this is the major K-point band, and there are shaded regions, very light shaded regions, on the left and the right-hand side. And you can also see this clearly when you take a KS-KY cut, and you can see this is the major K-band, and you can see this shaded region on the right and the left. And this actually agrees very well with our simulation. All of them are actually indicating that we do observe a moiré replica for the valence band at the K-point in the TMDC moiré structures. And this is actually special thanks to Professor Zias Shen and his postdoc Paulina, who kindly shared with us their beam time. Another thing that we are trying to do beyond the regular ARPES is the spin-resolved ARPES. For spin-resolved ARPES, it's a great technique to give you the spin signatures of this band. But the fact that spin-resolved ARPES is also very tricky because the spin filter is very inefficient. You need to have a significant amount of photoelectrons to reach into the detector to have significant signal-to-noise ratio. So spin-resolved ARPES is something that is very hard to do with very small samples. So now we can make a very large area twisted van der Waals structure, and we can actually collect very nice data for the spin-resolved textures of the band. And so this is just a KS-KY plot. That's the gamma point. This is the K point, and you can see two rings on top of that, and this is because of the two layers that are twisting. And this is actually a 67-degree twist WS2 structures, and we can clearly see that if you take a plot of the energy versus momentum at this cut, you will see the K band on upper branch and lower branch. And at each of the K band, you will see two actual features. So this will actually belong to these two twisted layers here. Okay, so all of this actually makes sense. But when we look at the spin-resolved structures, for example, in here, if I cut it vertically, you will see these four different sub-branches, 1, 2, 3, 4. And 1 and 2 are spin down, and 2, 3 and 4 are spin up. And if you move to the right-hand side, there is some some certain points that these two branches are actually switching the orders. And all of these are actually quite confusing to us, as we are actually trying to draw what will these band structures look like. So typically for monolayers, for example K point or K prime point, you would have two branches. One will be spin up, the other will be spin down. And if you overlay these two layers together, I would expect if you take a line cut on the left, I would expect the spin order to be down, up, up, down. And this will not be the up, up, down, down as we have seen experimentally. So there will be something that we don't really understand by just simply laying the spin textures on top of each other. So here I would also try to seek for any theoreticians to actually help us understand the spin textures in the twisted van der Waals structures. There seems to be a little bit more interesting things going on inside. So an additional thing that we are doing with this very large area twisted bilayer structures is we are also looking at this photo-induced ultra-fast phenomena at the interface. And in here, we are directly looking at the heat dissipation at the interface between the two layers. And the technique we are using is ultra-fast electron diffraction. That is a direct way to look at the dynamic motions of the lattice as a function of time upon photoexcitation. So in here, our bilayer structure is actually a MOSE2, WSE2 heterostructure at different twist angles. And so this type of measurements, any type of diffraction measurements, the signal to noise ratio is really dependent on the diffraction volume. And if you're looking at the monolayers, it's essentially just the size of the monolayer. As I've shown you, we can actually create monolayers and bilayers with the size of millimeter to centimeter scale. So we can actually put them onto a 250 micrometer by 250 micrometer and this thickness of 10 nanometer thin silicon nitride film. And this type of very high quality large area structures can allow us to see up to 10 orders of different diffraction orders in the ultra-fast electron diffraction screen. And we can actually see these diffractions for monolayers, for twist bilayers at different twist angles. And in this experiment, we actually photo-excite one monolayer and then look at how fast does this take to pass the heat to the other monolayer. So for here, our WSE2, MOSE2 heterobilayer, we are rationally exciting the MOSE2 layer. So at time zero, when we photo-excite the system, the layer will heat up. And because of the Debye-Waller effect, the intensity goes down. And we can also do a linear fitting and extract in-plane mean square displacement value. And this is actually related to the temperature or how much we are heating for each layer. And MOSE2 layer is instantaneously heat up upon photoexcitation. For the other layer, WSE2, it does not have this instantaneous heating. It absorbs the heat from the MOSE2 layer right next to it. So as a result, we see a slower heating up channel. And this slow heating up channel, we can also see that in the similar types of heterobilayers, MOSE2, WS2, there is also a slow heating up channel for WS2, and we can never see this in isolating the monolayers, which indeed indicate that this slower heating up channel is from the interlayer heat transport. And now we can see the slow heating up channel for the twisted bilayers, WSE2 layer, and we can also map that dynamics at 4 different twist angles. And indeed, we see that dynamics is a little bit dependent on the twist angle. It becomes faster at smaller angles. But in general, this the time constant for the WSE2 heating is in the order of around 10 to 30 picoseconds. And we asked our theory collaborator, Professor Felipe Jonada, and his student Jonathan to help us calculate how much does the heat transfer from one layer to another layer. And they gave us a lifetime of 200 picoseconds. And that is actually quite long. And later on, they realized that in here, when you photo-excite the system, the electrons in the holes will undergo ultra-fast scattering with the phonons, and they will scatter between different values. That actually creates a non-thermalized phonon distribution that's highly polarized along the K point. And that non-thermalized phonon distribution was actually found to be extremely efficient in passing the heat from one layer to another layer through a phonon splitting process. And with that taken into account, they give us a much better value of around 15 picoseconds in the lifetime that agrees really well with our experimental data. As I have showed you that this is just our experimental estimation of the Debye-Waller effect, but we can also see a momentum-dependent distribution of the phonons just from the diffuse scattering background. So this was actually done in collaboration with with Dr. Achana Raja's student who helped us developing the code to analyze diffuse scattering. As you can see that this diffuse scattering, which is rising up of the background due to the scattering with phonons, and if this is highly thermalized, the diffuse scattering would be localized around the areas close to the main bright point. If this is non-thermalized, especially if phonons are highly localized at the K point or M point, you would expect this diffuse scattering to more spread out. And in here, we see dynamically that in the earlier time, the diffuse scattering is more spread out, and then in the later time, you see it's actually more localized in the area close to the bright peaks. That actually indicates a thermalization of the phonons. And this thermalization dynamics is also a little bit different between the monolayer and twist bilayers, and we also see some of the preferential distributions along the K point and the M point in the diffuse scattering. So how much time do I have?
5 minutes.
5 minutes, okay. Great, thank you. So now I'm going to switch gears to another topic. So for these moiré structures, if you put these two monolayers, one on top of each other, depending on the local atomic overlaps, you would have different domains, which we call them BA, AB, and AA domains. These different atomic overlaps regions will have different energies, and in reality, the moiré structures would undergo what we call a periodic lattice distortion that will make the domain with the lowest energy as large as possible, and minimize the energies of the higher and minimize the areas of the higher energy domains. This periodic lattice distortion would really form the shape of the potential energy surface in the real space, and that would actually trap the charge carriers. And this actually plays a significant role in a lot of the strongly correlated physics. So how can we really see this periodic lattice distortion? So one of the things that we have done is, again, is also electron diffraction. So if you have just these two monolayers isolated from each other and without any periodic lattice distortion, then you would expect that their electron diffraction patterns would be just superimposing the diffraction patterns of two monolayers on top of each other. But if we have this periodic lattice distortion that creates this longer periodic modulation of the crystal lattice structures, in that case, we would see this this actual satellite peaks around the main bright peaks, and that is actually what we see in here in this low energy electron diffraction. And there's monolayer twist, monolayer on bulk. We have monolayer peak and bulk peak, and this beautiful moiré superlattice peaks. And the reason why we see the moiré superlattice peaks just around the monolayer, we don't see much around the bulk, is because when we put monolayer on the bulk crystal, the bulk remains mostly rigid, while the top monolayer undergoes the majority of periodic lattice distortion, and that actually agrees really well with our simulation. And this is actually different than twist bilayers. In twist bilayer systems, you would expect these two layers to coordinate together to undergo the same level of periodic lattice deformation, and as a result, you would expect to see the superlattice peaks to appear around both of them. Another thing that you might realize by comparing our diffraction signal with the published data on the twist bilayer is that we are seeing a much stronger superlattice diffraction in our monolayer on bulk systems. And that may indicate that if you have only one monolayer that does the majority of the job, that one monolayer would undergo the periodic lattice distortion with a higher amount of distortion on its own. And we can also see that different amount of distortion just looking at the signal intensities of the piezo response force microscope. And the intensity of this is just probing the local strain and the local lattice displacement that creates a difference in the resonance feature of the tip. So here you will see that in our monolayer on bulk structures, the PFM response is more than it's almost 2 orders of magnitude larger compared with that of the pure bilayers. And that is a clear distinction that the periodic lattice deformation for monolayer on bulk is different than pure bilayers. So since I have very limited time, I'm just going to skip this part and just want to quickly show you this last piece of result, that in addition to monolayers and the moiré structures, we have also developed similar techniques to create two-dimensional monolayer nanoribbons. So in here, we are also using a similar type of exfoliation techniques. Instead of exfoliating from the top layer of a van der Waals bulk crystal, we are actually exfoliating from the sides of the bulk crystal. This side can have a lot of this parallel aligned steps, and now we are really exfoliating the monolayers of these parallel aligned steps, and that would exfoliate as parallel aligned single crystal monolayer nanoribbons. And with that, we can create a huge selection of different types of monolayer single crystal nanoribbons. They are laid flat and parallel, aligned with each other. That includes all of the TMDCs, HBN, MOT to WSC2, RES2, and here are the optical and AFM images of them. They also cover hundreds of micrometer size, and that actually allows macroscopic experimental measurements on them. So I'm just going to skip this optical property investigation. So we see a lot of the effects from the string, which the nanoribbons is more susceptible of. And we can also create nanoribbons of different directions depending on the original crystal lattice we exfoliate from. We can create nanoribbons of the zigzag axis, on the armchair axis, and also this transition domain between the zigzag and armchair, which we call that Caro nanoribbons, and all of them would have different selection rules or different symmetries in the SHG scan. So I feel like I'm already running out of time, right? Yeah. Okay. So yeah. Since I'm standing between you and lunch, so I'm just going to end now. And thank you very much for your attention. Here is my group, and thanks a lot for my only funding. Thank you for your attention.
Thank you, Fang, for the very interesting talk. So there were some questions.
Thank you for the very nice talk. So I think in the slides you showed the HBN one method. Can you comment on that? Is it using a different metals, and do you get monolayers of HBN?
Yes, we got monolayers of HBN, and the reason why HBN, let me just quickly go to the HBN slide. So HBN indeed, yes, we use different metals. We use platinum, we use copper, we use nickel. For HBN, the tricky part for HBN exfoliation is the interlayer van der Waals force is stronger than TMVs. And also the interaction with gold is weaker. So it turns out that the platinum is more efficient exfoliating thinner layer of HBN than gold.
Thank you.
So I think I speak on the behalf of other experimentalists as well as what I'm saying, that this is making my mouth drool, and I'm not talking about lunch. This is just really cool results. I'm wondering though, I mean, it seems most of the work you've shown was about heterostructures with like bilayers. Could you do the full encapsulation with HBN, or at least have a bottom HBN layer to kind of have a regular device?
You mean if we can we put these bilayers on an HBN for a regular device?
Yeah.
Yes, we can. So the challenge for that is we cannot find a large enough HBN. It's usually for the device, people use tens of nanometers thick HBN from exfoliation. That
Here
size
you
of
have
HBN.
1 millimeter.
This is monolayer. This is not for device. Device will need thicker.
Okay.
Yeah, this is too thin. There will be too much tunneling, and the device won't work, unfortunately.
I have a question. So here you have a great recipe for transition metal chalcogenides, and yeah, you know how to deal with this. So now if you want to apply the same technique to materials that are still van der Waals, but let's say magnetic or CW, I can envision that in those materials you have a lot of stacking faults in the bulk. How do you plan to work with those? Can you do that, or are you hindered by the stacking faults?
Well, I don't think the stacking fault would be a huge challenge, but I think that there's still a huge challenge to work with magnetic materials or CW materials, as you have mentioned. The challenge actually comes from the chemistry. Here, we etch the gold with an aqueous solution that's a mixture of potassium iodide and iodine. And this is actually a little bit mildly oxidative. And the fact that this is actually in a water environment with an oxidative environment, this actually unfortunately precludes the applications to a bigger variety of materials. But indeed, we are also trying to find other ways to etch the gold. Like I try to convince my students to try potassium cyanide, which was supposed to be another very good gold etchant, but none of my students would like to risk their lives.
I was wondering if you tried to realize rhombohedral graphene structures. Rhombohedral stacking, like.
Yes. This other crystal structure stacking, we haven't tried them yet, but I don't think why it won't work. I would suppose it would work too.
Any further questions?
So you're saying for HBN you can only get monolayer, but not like thicker HBN?
We can only get thin layer HBN. We can get, for different metals, we can get HBNs from single layer to 5 layers up to 6 and 7 layers. But we cannot get thicker.
Why you cannot get like thick layers?
So that actually comes from the exfoliation mechanism. So the exfoliation mechanism is actually a spalling mechanism, which you actually have initiate a crack, and that crack actually propagates and along the crystal domain surface. And the fact that the HBNs, you can actually estimate the crack depth from the HBN's mechanical parameters. And the fact that the HBN interlayer, the HBN van der Waals interlayer force is so much weaker than the HBN intralayer bond, it is more likely that it will crack just into a very thin depth, and then it will just propagate along the van der Waals interface instead of going deeper.
Cool. I'm also wondering, can you use you pick up HBN first and use this HBN to pick up a TMD from TMD bulk?
You cannot pick up TMD from TMD bulk with HBN. HBN's van der Waals force is too weak.
Thank you.
Any further questions? If not, let's thank Fang again.
Thank you.